Good morning, everybody. Welcome to yet another edition of a Fine Power Hour. My name is Sean Ryan. I'm going to be your host today, and we're going to be going through another Power Hour expert mode, this time of the Advanced Lua Part 2. So again, my name is Sean Ryan. My contact information is below should you have any questions. What we're going to be doing is we're going to be going through, again, an advanced introduction, if you will, or overview of Lua. In the past, in the part 1, what we did was getting more down into the details, if you will, getting into specific functions, their applications, the syntax, example uses of that. I'm actually going to be stepping up a little bit level and kind of doing more of like a integration, higher level, putting it all together type presentation today for everybody. So with that, with the latest release of the NCD3 software, there is a new simulator in there. We've given a little bit of a preview of that in previous Power Hours, but this time we're actually going to be going through and basically going through every single one of the little buttons in there and giving a full demonstration of the entire environment. As we go through that, there's going to be a few different little aspects that come into play of how the variables that you define, whether or not you're doing locals and globals, we're going to go through that. And then we're also going to do a preview into sub-functions. And then as we go through with the simulator with that, we're going to go outside of that concept a little bit, and we're actually going to show how to feed and return values to and from sub-functions. Then we're going to discuss Lua Libraries and then delay example codes, basically introducing time dependencies into your code. So with that, before we get started, I do want to remind everybody that we have quite a few good references external to the NCD documentation. Again, Lua is a very, very common application language. And so with that, there's a wealth of information available on the internet. You can go to lua.org, and these two directories, these are a nice table structure of many of the different commands and usages and syntaxes available to this, of course, and then you can go on Stack Exchange and many of the other different online forums. Or, again, we're going to show this here in a second, and you can still go to the software advanced math and logic.pdf. So everything that I'm going to cover today for the good majority is going to be located in this document. For those of you who are not familiar, go ahead and open up NCD, go to Help, Documentation, and then scrolling down to Software, we do have the Software Advanced Math and Logic. So if we go ahead and open up that PDF, scrolling down through the table of contents, what we can find is the Logic Simulators tool here in section 5, or Roman numeral V. Click that, and it's going to go through again and give all the details of what I'm about to show here shortly. And of course, there's a good wealth of information. Closing that out and returning back to our PowerPoint, we're going to jump right to it. We're going to get into the simulator itself, not intending to do death by PowerPoint today. So we're going to cover the SPI list and how to view variables, the diagnostic and log windows. We're going to cover breakpoints, again, sub-functions at a high level. We'll go more detailed later. We'll show code stepping, viewing variables, and then I'm going to show a little bit of example usages of setting globals and local variables, getting the consequences of doing such. So with that, we're going to jump right into it. Again, back in our NCD environment, I'm going to go to configure. I have a pre-configured NCD file. It's basically just pulling a relay and nothing else. It's just I have one SEO client port set up here, so we're pulling a relay just for some points. Coming into our Lua environment, again, we've done a preview in the past. I'm going to skip some of the basic Lua programming stuff and focus again more on just the simulator itself. But to go against what I just said, in our inputs, you're going to notice that, again, everything that's available is on the left and everything that I want to bring into my environment is on the right. And so I'm going to take a few liberties and I'm going to go ahead and just add a few points. We're going to use these as some example code. You'll notice it has the point name, the event type, deadman, min max, and queue size. And the rest of this is all blank on the right. Keep that in mind because this is going to change. And then same for our outputs. We can go ahead and send one over. And then our logic inputs and outputs all look the same. This is where we're going to be able to define these points. So what we're going to do is we're going to discuss how to simulate something. So we need to first just create some demo code, if you will. And I'm going to go ahead and add this one, this add3. We're going to make this a timer function that's going to run every second. And you'll probably get the idea of I added these points, so we're going to go ahead and just do that. What we are going to do is in here, I'm going to go ahead and define a variable, local. Now remember this because we're going to come back and discuss the advantages and disadvantages of using local rather than just calling it total. So keep that in mind for later. And after we have that defined as a local variable, we're going to go ahead and say total equals orion.getPoint. And I'm going to go ahead and do this. I'm going to use my cheats since I already have these points in here. I'm going to click. I'm going to say value. And I'm going to just be lazy as I am normally. And we're going to go ahead and copy and reuse this code. So we're going to go ahead and change that to B, and then we're going to go ahead and change that to B, that to C. And now we have the syntax of adding three currents together. And lastly, we need to set that point to something. So we're going to go back to logic inputs. I'm sure you guys will know this will be the total amps. We're going to go ahead and define that point. And now I can say orion.setPoint. I can go ahead and do my syntax here of name equals, I'm going to go ahead and put total amps. I'm going to go ahead and do value equals total, and then online equals true. And so there we have our Orion set point, no code errors detected. And this is, again, going to run every second, pretty boring, pretty basic, but what we're going to do is we're going to use that as our example code now for demonstrating the simulator. So what I can do is, you guys may have noticed this button up here in the past. We're going to go ahead and simulate, and this is what's going to change the look of our environment somewhat. So click simulate, and we get a bunch more buttons and functions that appear over here. When I click into my inputs, you'll notice again some new cells have appeared in this kind of bluish gray color, showing that these are live. And so what we can do is, starting through this, we're going to just show how to view and set variables. So the first thing that's happening is it starts in this paused mode, if you will. We've got it stepping through lines here, and you'll see it's just on this function so far. And so if we come through and we click this play button, now my code is actively running. One thing that I needed to mention too is that as we're doing this, within the NCD3 environment, NovaTech is pretty proud of this. We were actually able to get very, very close to running the actual Orion process engine. So I'm going to say, just kind of arbitrarily picking a number, this is in the high 90-ish% of accuracy as far as what this is going to run in the simulation environment compared to what it's going to do on the actual Orion when you get it there. So it's so far, even throughout all my testing, it's ran almost perfect for me throughout, the many, many different advanced applications that we've come up with here at NovaTech. And so what happens is getting back to this, as this code is running, this add3 timer allows you to simulate values on the fly. So again, you'll see up here it says run, and I'm able to come right back to my inputs, outputs, logic inputs or outputs, and come into these values, double click it, and it's going to open up this box for me. And this allows me to now force values almost just the same as if I was on the Orion itself. So what I can do is I can go ahead and add a fake current in here. And you'll also notice this is kind of like the change common attributes tool. As soon as I type the value in here, you'll notice that that green checkbox appears, meaning it's going to be forcing only the value for me. If I come and check the online, that's going to force the point online. And so at this point, we can click force value, and you'll see that it came online true. It changed it automatically for me. And if I come over to my logic inputs, you'll see that it's now updated by itself to a value of 1, 2, 3, adding all these currents together. So now it gets a little bit annoying. I've got my inputs over here, and if I want to check over to my inputs over there, I have to click back and forth. So that brings us to our very first tool, the toggle spy list. If I open this one up, this is going to allow me to, you'll see I have some remnants of prep, it looks like, but normally it's going to start like this. And what we're able to do is actually go through any of our points like this, and we're actually able to drag and drop points of interest that we want to keep visible, just like so, pardon. And so we're actually able to view as many points of these, again, from different windows, all within the same window here, within the spy list. So we're able to come back, and we're able to force values again, just like we were doing before, and you'll see that they all appear within the same window. So that's the advantage of being able to use the inputs, the outputs, and the spy list. Now, one thing, we're not going to deep dive into this because we're not going to really focus on outputs today, but one thing I do want to highlight is that if you come into your outputs or some point that is going to trigger a data change event. So if we come back to our events and we had one that was of event type data and either an output or an input was triggered to that, as you force these points, in order for them to trigger the refresh function, if you change just the value in the online, that won't necessarily trigger that function. You do need to update the date and time so that it sees the latest and greatest timestamp of, if you will, just so that it sees that that point has changed. Even if it's the same value and you want it to re-trigger that function, you just need to update the date and time string as well. Anyway, getting back to this function here, that is the idea of having the spy list. You'll see that you can also come through and view reports, and so you can print this out if you like, and then you can also come through here and this will change the viewability of the window. So closing this guy, we're going to jump right into the next thing. So
hey, Sean, Clark.
Yep.
Just a quick question. For the simulator, how does it work when you have an external file? Let's say you have another file and you have the require code, the beginning of the Lua code, and then it references another file on the Orion. How does the simulator work with that file? Do you step through that code too, or no?
Yep, we're going to get to that a little bit later with the libraries, so I'll preface ahead a little bit, totally fine. If there are dependencies on there, as long as the files are within the same directory as the, I'll call it the base.ncd file and the base.lua file, usually the code is scripted to look into that file for it as well. If there's other files that are buried in different, like say the Linux structured directories, then that is something you might run into issues for. I have had to kind of had a simulator version of code and then also an Orion version of code, so because we're testing here on a Windows environment rather than a Linux, so you might have to tweak your code to get it to simulate correctly if you're going to that complex of a level. But otherwise, for the basic things like referencing just, you know, Lua libraries and whatnot, as long as they're in that base directory, they should be okay.
Okay, thank you.
Mm-hmm. So the next thing that we're going to get to is breakpoints. So you'll notice in the past that I clicked the play button, if you will, is what I like to call it, and it's stuck in the run mode. If I go ahead and click pause, this isn't going to make too much sense at this point. So we're going to modify this code here in a second and kind of jump ahead a little bit. But when I hit pause, you'll notice that these other tools up above ungray themselves. We have the first one being step into function, and these are a little bit self-explanatory to a point, but hopefully the demo will make these a little bit more clear. But we have step into function, we have step over function, and then we have step out of function. And then we also have breakpoints. So this first one here is toggle breakpoint, and then this one here is going to be remove or clear all the current breakpoints that you have. So the breakpoint, what I'm going to do is if I set a breakpoint here, and then I click run, you'll notice that my little yellow arrow, which is saying where the simulator was at like the specific line of execution that it was going to hit, stopped at this point. If I clear this again and I move it up here and I click run, you'll notice it just ran through this function again and it stopped here. Breakpoints allow you to isolate sections of code that you're in and then see what's going on at that specific point in code. Since we're not running at human speed, we're running at computer speed, which is super fast. That allows us to, kind of get a glimpse of what's going on at that specific point in time. We're able to go in, monitor things like the different logic inputs or variables that we're defining and whatnot. And it helps us for debugging and testing purposes. So that would be the idea of I can click play again and it's going to continually stop there. Or if I get it to stop at a certain point, I can then step little by little. So if I click step into function, it's already in a function and it's going to just go to the next line within that. So now it's ran this command. If I click it again, it's going to now trigger that point, go on and do this step. So I'd be able to watch each one of these lines execute. So if I were changing my values in this, I would be able to monitor my total. We're going to come back to this in a little bit. And then I would be able to monitor what goes into total amps. So the next thing that we need to do, we're going to kind of blend a few concepts together into this whole demo, if we will, is we're going to discuss the idea of subfunctions. So subfunctions are a great way of reusing the same block of code over and over again, just so that it cleans up your code and makes it easier to reuse things rather than having to retype over and over again. And then this, of course, is a nice foreshadow into the use of libraries going on in the future. But what we're going to do is, if we end our simulation, because now that I want to modify my code, I can't be in the simulator at that time. In events, we've defined default start function and add 3. To declare or define a subfunction, we don't need to do anything in this environment. All we need to do is follow this same syntax as something else that we have as an example for, but we can just do function, and then we can call it my sub function, and we can do this, and then we give it an end, and now whatever we want to put into our sub function, we're going to go ahead and just declare in this block. So now how do we call that? It's just a matter of coming back up here, and I can just call this reference. Oops, sorry, knocked the microphone over there. And so I can take this my sub function, and as this code executes, it's going to go ahead and define just as it did before. It's going to call this, and this function will now jump down and repeat this code, whatever I have in here. So I'm just going to go ahead and give it some dummy variable name just so it does something, and I can do a orion.PrintDiagnostic of, we're just going to call it 1, 2, 3. We'll give it a string. And so what's going to happen here is that every time that this runs within my diagnostic window, I've defined a variable that's not doing anything. We're not even calling it, and it's going to print this in the log. So if we go back up through and we simulate and we go ahead and clear our breakpoints, I'm going to go ahead and play. Then I'm going to pause it, and you'll see it just happened to stop arbitrarily at this point in time. So what I can do is, if I go into, again, my step into function, it's going to go line by line, and then it's going to see that the next code is my subfunction. So if I click into function, I'm going to be able to watch it jump down into this environment. I'm sure you can guess is that if I go over function, it's just going to skip this entirely. The code will still run, it's just I'm not going to debug down into there. So if I click this and I go into function now, you'll see it jumps down into this subfunction. Clicking once again, it's going to end that subfunction, and then it's going to now end my add3 timer. Now, if I set a breakpoint here and I click run, that's going to instantly bring my cursor to here. It's going to break out of that run. It's going to pause again. So now what I can do is I can click step over function. And let's go one more time. And you'll see it hits my subfunction, and it's going to go with one more click. It still executed this code down here, but it still didn't jump into there from a step-by-step standpoint. The last one, just to not bore everybody with this bit, is that if I had my cursor down and I was inside of a subfunction and I wanted to quickly run through it and get out of it, I can actually use the step out of function tool, and that would have brought me right back to this endpoint and gotten out of there. So you can use it for stepping into and out of subfunctions. Of course, this is the most basic level of what I've shown so far, but that will get us, so as you go subfunction to subfunction to subfunction and start really going down the rabbit hole, you can use that to your testing advantage. So the other thing that I want to show is we've done a little bit of a preview here. We did the orion.print diagnostics. Over on the left side, you guys might have noticed that the debug window appeared. So this says nothing more, it just says choose a debug subnode. So we have the diagnostic output and the log output. Again, these are going to represent exactly what you're going to find on the Orion, whether or not you go to the text-driven menu, the NovaTech shell, go to view communications and view the logic engine itself. That is what's going to appear as if you were viewing the diagnostic output. On the contrary, if I were to have done a orion.PrintLog for statements that would have gone to the log of the Orion itself, you can also find those outputs in this window. Now you notice the windows themselves are very similar. We have the options for actually flip-flopping the order of this, so whether or not you want the newest entries to appear at the top or the bottom of the list. So in this case, you'll see that the latest entries are appearing at the bottom, kind of similar to what you'd find as if you were in one of the hyperterminal PuTTY or even the NCD window itself. And then we have the option to copy everything from this to the clipboard. We can basically export or save this. We can clear it. And then we can also float this window and bring it out if you want and have this just go somewhere else. So this is another little handy tool as you're going through all of your debug stuff, so that way you're able to watch this, maybe some of your inputs, outputs, etc., and go through there. And of course, you can redock it by clicking that window. So the last thing that we want to, or that I want to cover, is the idea of these last few tools. This one's a little maybe useful to some. I don't find it as useful. The call stack is the order in which the simulator in this case, or the Orion process, of what it's going to go to next. So if at some point, so I find it a little difficult to use in human world, but if you have many different interrupts coming in and timers and a lot of different functions, and you're just curious to know what is going to be called next, this is the call stack. You can go into this window, but the more important one is the XY tool here, or the view variables. This one gets a little bit interesting, and I'm going to change all my code here to kind of go through the idea of why we want to define variables in certain ways. And so if we click this tool, it may seem a little bit cryptic at first, but we have our local section and then we have our global section. Locals are local variables, global are global variables. You'll notice that since my cursor is still within this function add3 timer block, since I defined my total, coming back to my earlier seed I tried to plant, since it's called a local variable, or defined as a local variable, I should better say, it's defining that variable right there. Even though we don't have total defined as, of course it is set to this total amps point, right? But we have this floating variable, if you will, within the programming called total. We're actually able to see what the stored value is of total within this view variables. So if you have, again, things defined as local variables, as long as you're within that same block, you're able to go back and see what it's at. On the contrary, we have global variables. So no matter where you are within your code and your code engine, you're actually able to come in and see this stuff. Now, I haven't defined any global variables yet, but you will notice that there's a few things that are just predefined as part of the Lua package or Lua environment, such as just pi, the max integer, all that stuff. So if I called math.pi, even though it's listed as a function over here, that's actually the reference of where it's coming from as part of that math library. So I can, at any point in here, I could do and simulate, I can do a print math.pi, and I can simulate that, and I can run it, and I'll run it a few times just so that it goes through. And if I go to my diagnostic output, you'll see that it printed the value of pi, because that is defined again back in my live variables. So what we're going to do about this fun stuff is we're going to go to the idea and the consequences or benefits, depending upon your application, of defining things as locals or globals. So we're going to end this simulation real fast, and I'm going to go back to my events, and we're going to go ahead and change this one to function 1. I'm going to do that, and we're going to add another one. We're going to call it function 2. I'm going to create that, and we're going to go into our timer. And so now what we have, as I clean up my code here, is two function blocks, if you will. They're each running a second apart. And what we're going to do is we're going to define variables within them. So the first thing I'm going to do is go to the idea of creating a global. I'm going to call it my global var, and I'm just going to set it to something, 1, 2, 3. Now notice that I did not define it as local. Local, you don't want to have a local global, basically. That's the idea. So we're going to go ahead and define it as this. Now, if I come into my functions, I'm going to define this local var1, and I'm going to say that equals some number, and I'm going to come down through local, I'm going to call this var2, and I'm going to say it equals, I guess, 7. That's what came up on my keyboard. So what's going to happen is now we want to see these. So we're going to go ahead and go orion.PrintDiagnostic. And I'm just going to go ahead and do var1. And you guys probably know what's going to happen here. And if I go this var2, it's going to print everything just fine. And the reason that to kind of step back and go to more of an explanation, what happens is when we define variables as globals, they're essentially available everywhere within the environment, no matter if I'm at the high level, still within the main programming block, or if I have stepped into my various functions. If I define a local variable, again, I happen to be an engineer, not a computer programmer, so this is my interpretation of it all, is that the local is a better way of using memory, and it really makes this more of a temporary definition. The globals, once you define them, they stay in the memory and the environment basically until we reboot the thing. If we define locals, every time that this function timer is called, again, once a second, it defines the local variable, takes up some short-term piece of memory, it runs its code, and as soon as we hit end, we discard that memory block, and it's now re-available, if you will, if I can make up words like that. Every time that this function is called, basically when we define a local, the process finds some chunk of memory, we define it, as soon as we end it, it's gone. We have to redefine it every single time, but it's clean. It leaves that memory available each time. So if we run this, simulate, run, and we watch our diagnostic output, I'm sure, and we clear our breakpoints and run it, you'll see it's just printing 345 and 7, 345 and 7, 345 and 7. Cool. So sorry, I meant to click pause. If I create a breakpoint within a specific function like this and I run it and I go to my variables here, you will see that the local that's defined here is only variable 1. We don't even see variable 2 here at all because of what I just explained of it's discarded, it has to be reinitialized at each time. So var2 is non-existent at this point. On the contrary, if we jump down into the global environment, you will see that I have my global variable that I created defined as 1, 2, 3. So what I can do is I could do an orion.print diagnostic of my global var, and of course I'd see 1, 2, 3 in there each time. Pretty basic at this point. As a example of now breaking this, I'm going to go ahead and remove this entry, and we're going to try and print variable 1 from function 2. If I simulate it and I clear my breakpoints, notice that as you go back and change code and whatnot, every time you end the simulation, go back and make entries, your breakpoints will remain, so that's helpful for testing. But if I come through and I click play now, and it's running through, and I go to my diagnostic outputs, I'm not getting anything. Nothing prints. If I go to my log output, you're going to see that I'm actually, every second, I'm getting errors because as the code is trying to execute, this print diagnostic is expecting a string of variable 1, and it got nil, which is a non-existent value, and so therefore it essentially breaks the code. So that's kind of the quick examples of why we would want to define locals or globals as far as what we do within our code structure, whether or not we want those to remain temporary or be global. Now, if I remove my local definition here and I go back to my simulation and I print this, or play this, I should say, my diagnostic output, now it does work. Even though that this is defining a different function, the instructions are not local. It's not saying to discard it every time this ends. So this is kind of creating a pseudo global variable that I don't like a lot within my own coding preferences, but this is just to show that this works. So do keep in mind the consequences of whether or not you use local or not, or if you define them as a global out in this code. Now what's happening is that each time that this function runs, it's defining this variable. So after a while, your variables are going to get a little messy. So that's it for the intro portion, if you will, of the simulator here. So we went through, we discussed the SPY list, how to set points. I do want to remind everybody again, if you do come for these outputs, do change this date and time if you're testing refresh events, but this allows you to force points. We discussed the breakpoints, how to step in and out of functions, did a little preview of subfunctions, hint, hint, because that's coming up, and then we discussed the variables here. So jumping back to Death by PowerPoint, we're going to go into the idea of feeding values into subfunctions. And so for this, I have some predefined code, if you will, so I'm just going to do some nice copy and paste and do some explanations of such stuff. But it should work all the same for us. So if we go back to our environment, again, we're going to now discuss, I'm going to do a little housekeeping here just to clean everything up. If I go into events, I'm going to clear that. And we're back to this stuff. So what we're going to do is we're going to discuss the concept of subfunctions and how to, again, reuse code each time by feeding in variables to a function. So as I said, I had some predefined stuff. Here's a quick copy and paste of this. And what this is this is a subfunction of code that I called it control check. We had a customer who wanted to basically have an input that's monitoring an output contact or a result of. This could be a 52A and this could be a breaker control. And then of course what we want that commanded output value to be. So we have the input name, the output name, the trip close control value. And what this code does is, in quick translation, if you will, is that we have an Orion set point. So what we do is we define the output name, and I should have prefaced this a little more clearly. This is going to be, again, the Orion point name. So I may have fed in, 52A at whatever. You'll see in a second. The output name is going to be the exact same output name as if you were in here. And then the trip close value is going to be just a simple number, and this will make more sense in a little bit. But the idea is we're doing a set point of that output, of that defined value. We print that to our diagnostics and our logs, and then we wait. So here's yet another hint of what we're going to discuss in a little bit of our time-dependent code. This is a very ugly style of code, great for testing, great if you don't have other important stuff, I'll say, going on in the background. This is basically a loop function or a processor burn. So this is going to eat up 3 seconds, if you will, of your total processing time. So nothing else within your Lua engine is going to happen because it's going to be stuck in this section for 3 seconds. But this does introduce a nice 3-second delay or whatever you define in this number. So we'll keep this in mind. You guys can reference this for code should you need it later. But what happens is after we send that command, we wait 3 seconds. We then define a local of temp input value, and we go and get the value that came back from that 52A. So we're basically saying, did that breaker actually open or close? Did we get confirmation that it happened? Then we say, if the commanded value equals our monitored value, then we say output and input confirmed for our control. If they don't match, then we can set a point called command failure at logic, which I did not define, which is why I have this error down here, but you get the idea. So this is a quick thing. This is, again, our sub function. So even though this makes no practical sense, if we came back up to our function one timer, what I can do is I can call this function. All I have to do is do a nice little copy paste out of laziness, and I do control check. And now all I need to do is replace these names with the actual values I want to feed in. So if I go to my inputs and let's just say trip, this doesn't make a whole lot of sense, but you guys get the idea. If we send that over, if I replace this value, I'm feeding it in as a string. So this value, as it's passed into my actual subfunction for input name, will be treated as a string through and through. The output, if I come to the outputs, again, this doesn't make a lot of sense, but we'll just pretend remote bit 1 is monitoring it. We'll go ahead and just dump that in there, and then we're going to send in the value. So if I send in a 0, essentially this is horrible code because this is going to send a trip command to my breaker every second, but for the demonstration purposes, that's how we can reuse this code over and over again because the blocks are dynamic. Whatever you feed into it through this is going to be reused. So if I wanted to use this same structure, I could come through control, and if I wanted to do the exact same thing to something else, you get the idea. I would change this point. Again, this makes no sense, but I would change that to another point, change this to another point, and I can reuse that code over and over again as it's passed through. You just have to keep in mind that as you define these points for what's fed into these subfunctions, is they're just generic names at this point. You do have to keep in mind of how they're going to be passed through, whether or not they're numbers, strings, or whatever the data type is. So that's the idea of being able to feed stuff, speaking very generically, into subfunctions. The next topic is essentially the reverse of this, is how can we use sub-functions and get stuff back from them. So I just so happen to have yet another block of example code. So I'm going to go ahead and grab this. And the quick translation of this, this happened to be some example code of what we used at our UBBA conference. If you guys paid or if you received word on that, of integrating the NovaTech with the private LTE environment that's going to be coming out in the next few years. Products exist now, of course, but as utilities start to adopt that, this was used for some of our proof of concept. And so what we had was a device table. This is a very shortened version of it, if you will. This was just a lookup, if you will, but this table had a defined input, a defined output, a COM fail for that device, and then just a nice little text label that was used on the HMIs. What we had was, we're going to go ahead and move this up here for us, redo this. And what we had is basically a sub-health, if you will, monitor. So this thing was running every 1 second, and we had it running through a COM fail monitor. So this was just monitoring the COM fail status. So what we did was, or what I built was this function that was a COM fail monitor. Every time that this runs, we define 2 points. We have a COM fail flag, which is either just a yes or no, a 1 or a 0, and then we have an overall counter. So every time that this runs, we have a 4 key and value NI pairs. And basically what this does is it runs through and it looks at the COM fail points that are defined, the third value inside of each row through this table. And it looks to see what the value is at that point as it goes out and does an Orion get point of, say, COM fail at this device. So if that point is a 1 and it's in fail, we go ahead and set the COM flag to a 1. That way, if they're all good, we'll never set this point. It'll remain at 0. But if any single one of them, kind of like an OR function, if you will, triggers this, we'll get a COM fail flag. And then that will be the true or false. And then we also have the COM fail count. So each time that that goes through the iteration, it will take its previous value, add 1, and we'll get a counter of how many devices are actually failed. So I want to be able to run this function each time and then send whether or not I have a true or false and then the count out. So the syntax or the command is return. Whatever I want to, if I have something inside of a sub-function and I want to send that back out of the sub-function, I need to do a return. I can do just one variable or I can do multiples. And so in this case, you'll see I have 2 and they're separated by this comma here. COM fail flag, COM fail count. So every time that this function runs, even though I didn't feed anything into it, I can still get stuff out. So coming back up to my function timer, my flag, whether or not I have a general one, I define it as, again, whatever variables that I named, if you will, whether or not they're globals or locals. I didn't really put too much thought in this example, but flag, because it's the first before the comma, is going to become the same value as COM fail flag that's returned from the function. Same idea as we have count, that's going to be returned back from COM fail count. If I come back to my PowerPoint and I go to this next function, or next slide regarding the returns from sub-functions, this is yet just another example in a lot smaller sense if this makes it a little more clear. Oftentimes we'll use I liked this example. This is just something I stole from the internet, actually up from this same directory. But the string global substitution function, for example, it actually returns 2 items, or 2 values, if you will. The first one, or I should say the second one, is actually the count of the number of strings that were replaced. And so I thought this was a great use of, in this example, it was if you feed in a string, whatever value of the str string is, it will actually count the number of white spaces. Just notice that's a space, that's a space. Even though it's substituting a space with a space, it still does a count of the number of replacements, if you will. But since you're replacing it with the same thing, it just gives you a count of the number of spaces. So that is the second return. But if we didn't care about the first one, again, this shows the use of that comma for going through. You can actually use the underscore character as a dummy variable. So you can just say, I don't actually care about the first one. All I'm interested is in the second. So if I do an underscore, comma, and the count, that will give me an example. So that's a use of, again, after using the subfunction for returning stuff out, how do I want to now use those returned variables? Chi, any questions so far? Sorry, I know you're probably on mute, but anything over all this stuff we've covered so far?
Not right now. There's some that we'll need to answer in the post email, but we're good for now.
Okay, thank you. So jumping on, the next thing that we want to do is the idea of Lua Libraries. So the instance here is that the short syntax, you may or may not have seen these in some of the Lua scripts that NovaTech's created or in others, is that we have these statements of require and then some library name. So we're going to do a quick demonstration of how to define our own library, but you'll also notice that there's other ones such as the built-in required dates and maths, or the Lua SQL library for getting into the Orion database. What I have found is that you can just put, Lua had a little bit of a change in the last few versions, so you may have seen this defined or written first as a variable equals require this. I've now found that this shorthand version works. Both within the simulator and within the Orion itself. So all we need to do is just say a require and then the library name. Again, we don't need the .lua or .lua extension after it. All you have to do is just put the name of it. Now, again, in the simulator, I've found in the Orion log will tell you if something is missing for sure. But again, and thanks to Chi's question earlier, that as long as the libraries and files that you create are in the same Windows directory for the simulator as your main NCD and your main.lua file, it'll run just fine. So if you have those, you can go ahead and put them in there and the simulator will find those. Now, the date, the math, and the Lua, these are all built into the Orion already, so you don't necessarily need to include those for sure, but at least for the simulator, these ones will need to be in there. So what do I mean by all this library stuff? So if I come back to the NCD environment, and we're going to go ahead and clean some of this stuff up. And what I'm going to do is we're going to define a file as test library. So here's the code that I'm going to be working with. It's a little bit out of order, and we'll see what's going to go on. So I'm going to have a timer, and we're going to just have it do this test print function. And down below, inside of our library, we're going to have a test print function, and it's just going to say hello. It's pretty simple, pretty basic, pretty boring actually. But the idea is we will show how to create a library file and reference it all. So what I do personally is before even my default start function and anything else, I'm going to go ahead and place that require function. So this is the first thing that's going to run whenever my Lua code executes. It's just going to say require my test library that we're going to define. Inside of our actual function one timer, we're going to go ahead and do this test print. And taking this away for a second, this with our defined library is perfectly valid enough. So if we come back, it needs to reference this test print function somehow. And if we don't have it defined below, it's going to need to find that in its library somehow. So what do? We're going to go ahead and go to, I just happen to have Notepad++ open on the side. And so we're going to go ahead and go a new file, and I'm going to do a nice cut and a nice copy over to here. And one handy thing is if you're working in Notepad++, there's just a little tangent or aside, you can go to language and you can go to L for Lua, and this is all built in, and it's going to start to look the same, similar-ish as if it were over here inside of the NCD environment. And of course, that's correlated or referenced directly to the Lua language itself. A few extra little tools you can expand and all this, have some fun with it. But what we can do now is I can do a file, I can do a save as, and since I'm running everything off of my desktop right now, I just need to name this file exactly the same as my reference that I did up here. So as long as I put this, again verbatim, test_library onto my desktop, now this code should execute just fine. So let's see what happens. I'm going to go ahead and save this. Maybe it'll work, maybe it won't, maybe we'll go to my Orion. So if we go to simulate and we click run, if I go to my diagnostic output, it just prints out hello, 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 hello every second, all because that library, if I minimize all this stuff, I have my powerhour.lua that we're working off of. Its base script, powerhour Lua, which again is just this stuff, and then because I have my require test library, I'm able to still have this section reference my library here. So the overall idea is, why do we discuss the library? It's again, well, a few great reasons really, especially in our applications. It's a way to simplify and clean the coding window, especially if you're using the same sub-functions over and over and over again. If you want to take the previous idea of, again, what I showed with the sub-functions, if you're going to be reusing the same similar block of code over and over and you want to dynamically feed in different names or reuse that code again to retrieve variables, you can of course store them in the bottom here, or you can keep them separately, a little bit cleaner in a library file like this. So all the sub-function stuff I had done, as long as I would have done a required test library, I could have kept all that syntax over here in this file and we would have been just fine. The other great reason for doing this is that you can define especially if you're a larger company, some engineering consulting firm and whatnot, and you wanted to reuse the same stuff over and over and over again, and kind of keep that as a standard, if you will, so that this library remains static and unedited. And then that way all of your, I'm going to call it your dynamic or unique stuff to a particular substation or project can then be defined over in this environment. That way, as you're going through and if you are troubleshooting, it will actually help you figure out where that error may or may not be. If your known library has been tested over and over again and is known to be working each time, that has a pretty good indication that your problems may be over here, or again, just for maintenance, future changes, whatever, it keeps your changes in just one particular file rather than all of your static library stuff. So that's a great example of being able to do this. I'm actually going to try one thing, if we will. I'm just going to go to a step. I'm going to go to test print, and you'll notice that as going back through on this diagnostic stuff, I was actually able to jump over into my library or required referenced file. So if you guys may have missed that, let's do it again. If I set a breakpoint here and I run to that, you'll see I'm on test print in the pause mode, but still running through. It's calling test print, even though test print doesn't exist in this main powerhour.lua file. But if I go into test print, it will find that within test library and still be able to step into that syntax or that code written there. So another cool feature of the library, and then one last little hint of being able to do that in the simulator. So I go and simulate, takes me back here, and that even though it was a lot of tangents, references, and everything else, is the end, if you will, of what we wanted to cover as far as the simulator goes. Can't see if there's any questions, feel free to jump in, but we're going to jump in to the kind of last section of my code examples, if you will, and the applications of it all, is the time dependencies. So again, I dropped a hint and kind of showed it earlier of what to do. This code, again, is used, I say best, if you don't care about the time dependencies of other stuff or other functions or anything else. Maybe you have some calculations going on the background, but if they can wait 3 seconds, you can use this code. It's again, it's a processor burn style code, if you will. It gets stuck in this loop until we finish something. The example of that is that if we come back to our timer now, and I get rid of all my requires, and this is supposed to be printing every second. So if I do a if I do an orion.PrintDiagnostic again, and if I did hello, but if I also came back and still put in that same wait logic, can you guess how often this will actually print? Everybody yell it out loud. Whoop-de-doo. So if I click simulate and I run that, and I remove my breakpoints and I run it, I'm sure you guys can guess, watching this code, what's happening here is that it's running every 3 seconds for me. Every 3 seconds, every 3 seconds, even though the function is defined to run every 1 second. So if I take this a step further, and we define something else, function 2, should have left it there really, and we leave that as a timer and it's running every second. If I do a orion.PrintDiagnostic and I say goodbye, can you guys guess how often goodbye will print? I have 2 different functions, totally independent. This thing's defined as a local. It's got a wait function up there. Everybody place your bets. And if I come through and I click simulate and I run this, I go to my diagnostic output. Even though that this is a second function programmed to run every 1 second, it still has to run through this and it's still waiting 3 seconds in here. So we're only getting the goodbye function to run, again, every 3 seconds per my timestamps. So again, that's just the consequence that I want to show of using this time delay logic. If you don't care in your application that this is running slower, again, this is a horrible idea to use this as running every 3 seconds in this example. Obviously, if you wanted this to only do 3 seconds, please just go ahead and change the timer itself. This is a poor example of it. But if you're using this in the previous sub-function example like I had, if this was on only a data change or an interrupt style function, again, as long as that only ran once and you didn't care about these other timers executing on time, then this is an okay function to use. It's just not the best. Our next example is, bear with me a second while I do some formatting here, is, I got to scroll back around. Clean this around. Go ahead and get rid of function 2, and we'll delete that. Here's a bit of code that this is I believe this came out of Arizona. This is some code I wrote for a customer that basically wanted to monitor a reported fault distance. They had a lot more. I cleaned this up for our demonstration here, if you will. But the idea is that they wanted to have a fault distance be reported for 5 minutes, which is, as we'll run through this in a little more detail, but they wanted it to be reported for 5 minutes, not be able to be interrupted by other reported faults in case multiples came through during that 5-minute interval. But then once that 5-minute interval expired, we wanted to go ahead and reset that reported distance back to 0. So the way that I accomplished this was by actually creating two subfunctions. The first is the interrupt event up here, so we'll kind of run through this. And then we actually had a timer function down below. So the way that this works is this was programmed as a data change style event. And of course, whatever points were mapped into this as part of the events would trigger this. And so what would happen is that this was for the particular 5001L relay or line, if you will. So that's the references that you're going to see in the specific point names. Of course, I'm getting a lot of syntax errors because I haven't defined those, but bear with the example. So the way that this works is as we run through this code, when this is triggered, if you will, we define two variables. We have seconds to reset and we have the distance. Now the seconds to reset is stored as an actual logic input point so that it's able to be referenced between these two and kept different. Could have defined this as a global if you wanted to, but we just decided to do it this way just so that it's also monitorable, say in the HMI or whatever else if you wanted to as well. So what we said is that if the seconds to reset is less than 0, then we're going to go ahead and do this. So again, that's as long as there's not something still present within that 5-minute interval. So as long as this is all clear, we go ahead and say fault detected. We're setting our logic point to a recorded value from the relay. So we set this logic point, the timer, if you will, straight to 300 seconds. Again, this timer down here is running 1 second, so that's why we're defining it as 300. 300 seconds correlates to 5 minutes. Distance is equal to the fault location pulled from the relay itself. Then we say that distance value retrieved from the actual IED is going to be set to a logic point that we've created. So this reported distance at logic is equal to the actual distance. It's basically just naming a real value to another, and we're just holding it there. The fun bit that we did here is the orion.enable timer. So this function is actually set to a timer enabled false by default. It would look something like this, that timer, the interval, and then false. So it's not running at the initialization or at boot of the Orion. So once we use this syntax to enable the timer, this kind of becomes our countdown, if you will. So now that this block of code is active, running once a second, we say local seconds to reset, and it just references that same timer we defined as 300 initially up here. We say if the seconds to reset is greater than 0, meaning we still have something to do, then seconds to reset equals seconds to reset minus 1, and we go ahead and just set that point, and it's just going to count down every second, decreasing, decrementing, 300, 299, 298, etc. When that value finally is no longer greater than 0, and this function is called, we go ahead and say resetting fault logic distance value to 0. Then we do a set point of setting that reported distance back to 0. And then importantly, we disable that timer. So that deactivates this block of code. Now that this point is set to a 0, this can now be called again if the seconds to reset is less than 0. And then that way we could then trigger upon another fault after that initial 5 minutes. So the key bit about this time dependency here is that, again, we don't have any of the previous example of the processor burn, the loop, anything else. This allows any other code, since this is running once a second as its own event, any other code that you might have that also might be time dependent, just go ahead and still run on time. So that's another great example of being able to use this dynamically and be able to set points as counters. So you can change this, you can change the variables, how much it increments or decrements each time and play with it, but that sets the basis for how often you want something to run like that. Now the next or the last example that I have for doing time dependencies is that maybe it's not a relative time dependency that you want as the previous example, but maybe you want more of a absolute time dependency. So the last example that I have for you, as I clean this stuff up, it would be a function like this. This function was another customer request that wanted one of their accumulators or their counters to freeze and update basically at the top of the hour. So the way that we accomplished this is, you'll get the idea here, is just by using this top section of code here. The rest of it really doesn't matter. But what we define is using the functions down here and underneath Orion, we have the current time, cur time defined as the local time, and then we define the minute and the second. So what happens is, what I like to do is set an event so that this runs every 500 milliseconds, just ensuring that it runs somewhere between the specific seconds that we want. So ideally it would run almost twice a second, if you will, but it'll hit always once. And with that in mind, we say that, again, to accomplish our goal of having this code run on the top of the hour, we say with these minutes and seconds defined, if the minute is equal to 0 and the second is equal to 0, again, right on the top of the hour then we're going to go ahead and run and execute some code. Now again, keep in mind that you need to keep this interval short enough to ensure that this code runs. And then also, if you are using something as absolute as this and depending upon it, if you were to go back and use our previous example of the, what I like to call the processor burn logic, if this block of code were in some other function and this was basically stuck in that loop for these 3 seconds and coincidentally, consequently, this moment in time happened to pass, this code would never execute for that intended block. So again, that's kind of the consequence of using this code when you're using absolute dependencies, such as a code example like this. So with that, unless there's any other questions, I think we're going to jump to it. Tried to spare everybody as far as not boring them to death with Lua concepts. Again, like I said, we didn't go into anything too deep today, but tried to show kind of the higher level of how you might integrate everything that we have showed in the past, and then of course be able to test that thoroughly and properly within the NCD simulator that's again available in the latest version of NCD 3.37. So to continue the rest of our PowerPoint stuff, again, you guys have probably seen this quite a bit, but for those of you who have not, again, if you have any questions or you're looking for documentation, examples, or especially the online webinar recordings such as this one that we just did today, you will be able to find those at power.novatechautomation.com. Go ahead and go on there. If you've not been on there before, go to the site. Please do request a login. It is a manual approval process, but we'll try to have that completed and you'll have access within a day or two of that. If you want a little bit more one-on-one information, you can still do the sales engineer booking.novatechautomation.com. You can find one of us and get, again, a one-on-one style consultation of that. All of us are available down here. And then, well, should have changed that slide. If you want to get a hold of Jeremy, go ahead and Jeremy.Anderson right there. But if you, again, if you need my initial contact, you can reach me here. Again, thank you all for joining today. I'm sure there were some questions in there. I will get to those in one of the post follow-up emails. We'll go ahead and get all of those questions answered and published to everybody. Again, thank you everybody for joining today, and we will see you guys again in 2 weeks for yet another edition of Power Hour. Thank you very much.